Welcome to yet another class. I'm Dr. B, and today we are going to be talking about the zero order rate law. We're going to look at that, the zero order rate law. That is what we're going to be looking at. Zero order rate law. And remember that we have different type of the order. We had discussed rate of reactions before, and we had mentioned zero order, first order, second order, and third order reactions. And today we are going to see how we can derive the zero order rate law. But it's important for us to know that this zero order rate law falls under kinetics. Remember that we have what we call thermodynamics and kinetics. Now, in kinetics, we have rates of reactions. Remember that kinetics as a topic discusses the relationship between rates of reactions, mechanism of reactions, and their various reactants and products. While the order of reaction actually try to see that it is a link between the rate of a reaction and the concentration of the reactants that take part in a reaction. Now, we are going to inform us that the zero order reaction simply is a reaction that does not depend, or rather a reaction whose rate does not depend on the concentration of the reactants. Okay, that means no matter how you increase your reactants, no matter how you reduce your reactants, it will not affect the rate of the reaction. We have very few reactions actually that exhibit zero order, and but as far as the reactions actually exist, there is need for us to understand how we can be able to derive the rate law and also see how we can possibly calculate the rate law from the graph. Now, let us see how we can derive the rate law. Now, if we are given an equation A to give us P, that means that this is of course our reactant and this is our product. Remember that for the rate of a reaction, the rate depends on what the concentration, or may not depend on the concentration, and for the zero order it does not depend on the concentration of the reactant, and this is the reactant. First, for you to derive the equation for the zero order rate law, you must be able to understand what the differential equation is. Now, you have idea, of course, concerning some little basis of further mathematics, and it's important for you to know that before you can be able to deal with both the zero first order and third order and pseudo order reactions. Now we look at the differential form of this equation. We shall write the rate equation, differential rate equation for this particular equation with respect to the A, the reactant. So we have minus D to A all over the T is equals to K to AO equals to K. Now this is simple. By this equation, it means that you are differentiating with respect to T. Remember that the rate of reaction has much to do with what the concentration of reactant with respect to time. And then this is the reactant, while this is the concentration of the reactant at zero order. Now, once you have this bracket, it means it's concentration. We are not interested in the reactant itself, but the concentration. So we rewrite this equation to rather carry this particular letter here over here. So we write the equation. We'll have minus the A all over the T is equals to K. By this, now this is our equation 1 and this is our equation 2. By this equation, we have been able to actually place and define the fact that we are differentiating the reactant concentration with respect to zero order with respect to T. Now, when we arrive at this point, there is need for us to do what? Eliminate the negative sign that we have here and cross multiply. So by this, we are going to multiply. So by this, we are going to multiply both the left hand side and the right hand side by what? Minus the T, which is this value. So when we do this, we are going to have what? We are going to have minus the t we are multiplying by minus dA O all over the t, okay, equals to what? Minus k dt. By this, it means that we have reflected, we have multiplied minus dt by both sides of the equation. And with this, we can conveniently know that minus minus is plus, so it will go. And then the t will cancel the t. We can rewrite our equation in this form very comfortably. So we can bring this out and have the A, okay, is equals to minus k dt. This is our equation 4. Now, with this, we have come to a point where we need to do what? Integrate. And that's why I told us that there is need for us to understand the basic integrations and basic differentiation that we have. Now, at this point, we are going to do what? Integrate. So, if we are going to integrate, so we are going to integrate, we integrate equation what? We integrate equation 4. That means we were going to have the integral of dA is equals to what? Minus the integral of k dt. This is equation 5. Okay, we are differentiating with respect to the concentration of A at 0 order and A, and respect to T initial and T final. We are differentiating with respect to this, integrating with respect to this, and here with respect to this. Now I want us to know that in our basic mathematics, the integral of the x is x. And if that is the case, that means the integral of the A will be A. Just like you say, it is 1. So we integrate with respect to their integrals. And if we are going to do so, that means that we are going to have, this implies that we are going to have A, which is this, and on top we have A, and down we have AO. This is the same thing like saying A, okay, which is this, minus AO is equals to this. Is equals to minus KT. Remember that already you have done what? Integrated this. So you have lost the differential signs that you have here. Now at this point that we are here, we can basically rewrite this equation what? Equation 6. Now to rewrite this equation 6 means that we are going to now concentrate on the basic concentration of the reactant while we pull the zero order to the right hand side. Now this means that we can also have A is equals to what? Equals to plus AO minus KT. And this is our equation what? 7. Now this is actually the integral form, okay? This equation we have here is actually the integral, okay? Is actually the integral form. The integral form of, this is actually the integral form of the zero order reaction. It is the integral form of the zero order reaction. But now, how do we get the rate constant from here? It has to be in a graphical form. So for you to be able to generate the graph for the zero order reaction, to be able to calculate your rate constant, you are going to rewrite this equation to take the form of y is equals to mx plus c. And to do that, our y is going to be this, which is what? Our A, concentration of reactant. Why we rewrite this equation? Because we are going to plot a graph of A against T, and this of course will be our C. So we now have minus KT plus what? AO. This now becomes our equation 8, this now becomes our equation 9. So at this point, you can see that we can now plot a graph of y. You plot a graph of y against what? X. And this is your intercept. So we plot a graph of concentration of A against what? T. Why this is the slope, this is the intercept. So a typical graph of that nature is like this. So you can possibly have a graph of this format. Why this is the concentration, this is the time. And here, of course, define your k, which is the minus slope. While here, define your intercept. Your intercept, which is what? AO. See? So, once you're able to plot a graph of this form, once the line of that your graph, the straight line runs in this format, you can be able to calculate what? The slope. It's just for you to draw a tangent, to take a tangent from any point of the graph, and then you calculate this. So this, of course, will be your y2, your y1, your x1, your x2. In the normal equation, of course, you know that your slope is going to be equal to what? It's going to be equal to your y2 minus y1 over x2 minus x1. So the slope that you are going to have, of course, is your what? Rate of reaction for the zero order reaction. Now, it's important for us to know that there are a few relevance, like I said, few reactions that undergo zero order reaction. And one of them is the iodization of acetone. Permit me to explain some of these things so we can be able to understand what we are doing. So the iodization of acetone is one of those reactions that obey the zero order rate law. And I said iodization of what? Acetone. Iodization of acetone is one reaction that obeys the zero order rate law. And this is CH3COCH3, okay, plus iodine, and it will give you, of course, it's going to give you iodine CH2 COCH3 plus hydrogen iodide. Now this is a typical reaction, iodization of acetone, that obey the zero order rate law or rate equation. Another equation that obeys this, or rather reaction that obeys the zero order, is the production of HCl. Okay, production of HCl. It's another type of reaction that obeys the zeroth order reaction. And this is, for example, hydrogen plus chlorine to give you 2 hydrogen chloride. This kind of a reaction also obeys the zero order rate law. I am sure that today, if you watch this video carefully, you should be able to derive the zero order rate law equation from the beginning, which is the differential rate equation, until the integrated form, and plot the graph, and at the end be able to calculate the rate constant and possibly the examples of reactions that obey the zero order equation. Beautiful class today we have. Please do not forget to subscribe to my YouTube channel. Don't forget to also follow my Facebook page. Do not forget also to like, to comment, and to share. Until next time, it is bye for now.